Okay, so the first thing I want to do is define what a north and a south pole is, because basically the goal today is to describe what effing magnets are and how they work, right? And if we have time, I've got a little video that I could show you about that. It's only a small part of the video. How many people have seen the video I'm talking about? Insane Clown Posse Miracles.
Yeah. Wait,
what?
Insane Clown Posse.
Did I say that? Yeah. ICP, yeah. Anyway, we're going to try to work our way up to a deeper understanding, sort of like they have, but let's start with something a little more basic. So concept zero is this. People found rocks and they call these things lodestones, and these are just naturally magnetic ore, okay? And they discovered that if you take a piece of lodestone, or even if you take like a little bit of metal that's been rubbed against a lodestone, right, and float it, and you can actually do this, you can take a needle and magnetize it, float it on the surface tension of water. A needle will float on water, kind of, because it'll just sort of like press on the surface tension, right? One end of that needle will always point toward the north, and this end is called the north pole of the magnet. So here's this nice magnet here, and what I'm going to do is try to float it on some water, okay? And I'm going to point it, so I actually did this one time, and it was actually pointing exactly north, and so when I floated it up, it didn't move, which was somewhat anticlimactic. So I pointed this in a direction that I know is not north, hoping that it will swing to the north when it eventually is not resting on the bottom of the Petri dish. There we go. Oh, look at that. Hello? You're supposed to swing. Swing north. Oh, there we go. That's kind of fun. And this is working because I've actually filled it so it's like brimming full. And it's basically frictionless. And if we point it some other way, it will eventually orient itself. It's really pretty strong force there. You can see it's going to damp down, but it'll eventually point north. And then people realized that pointed north, and this became a navigational tool, yes? Okay. Other ways to determine whether something is the North Pole, sometimes if you look at the magnet and you look at it very carefully, you can see a little N stamped in the end. Chances are that's also the North Pole. North Poles also tend to be painted red, yeah? Or they tend to have like in this magnet here, I'm sort of semi-joking, right? This magnet's got a big divot in it. All the North Poles are marked with divots in them, right? Like that, you know? Okay, so that's one way to figure out which way the North Pole is. Ultimately, the North Pole will point itself to the north. Now, let's see if I can get this off of here without spilling too much. There we go. Okay, so that brings us to the interesting topic of if we have a magnet, a compass, right, and we know that the compass points north, and somebody gives us a magnet, and we don't know the polarity of the magnet, like this is, I suspect, a magnet, okay? What we do, here's how you determine the North Pole of this magnet is, well, you could float it on water and see which way it points north, but that's way too time consuming, right? So what I'm going to do is I'm going to take one end of this and go, I wonder which pole this is. And the thing to do is actually bring it in from the side and see which side of the magnet likes it, right? Well, do you see that the North Pole of that one likes it? So the side that's toward there must be the South Pole of the magnet, yeah? Okay? Because north repels north and south repels south. So therefore, the north is being attracted by this must be the South Pole. Now we can further test this. The other end of the magnet should be the what pole? Should be the North Pole, so let's just try that. Sure enough, the South Pole likes of this magnet, right? Yeah? So on a compass needle, the North Pole points toward the north, okay, and the South Pole points toward the south. The North Pole of the compass is a North Pole magnet, and the south end of the compass, right, is a South Pole magnet, okay? Now, we're heading towards something, and this might shake some of your faith, okay? This might shake some of your faith, and I just want to, you know, it's a delicate subject here, right? Okay? But we can put the compass on the overhead. That's what I showed you, right? This is a shocking revelation, okay? If we think about the Earth, why does the compass needle point toward the north? Is it because the Earth generates a magnetic field? Yeah. Okay. By the way, your life, you're gonna register your life as like before you heard this news, and after you heard this news. You're gonna talk about your life in that way. Okay. Because here's where we're headed, right? The Earth, therefore, must be a magnet. Correct?
Yeah.
Yes. The Earth is a magnet. Okay. The Earth is a magnet. Now, if what we call the North Pole of a magnet always points toward the North Pole of the Earth, let's step back a little bit and think about what pole must be at the North Pole of the Earth, or actually over in like Nova Scotia. Yeah, the Earth's North Pole, right, must be actually a magnetic South Pole. Yes? Oh my God! Ah! Right? It's like, look up! Whoa! Ah! Sorry. Okay. There we have it, right? So, okay, so we've got a magnet on a pivot. I know it's exciting. I'll be quiet. All right, magnet on a pivot. Can everybody see the magnet on a pivot? We have a sort of a visibility. Can we see this? We got a magnet on a pivot. I need like something up here, don't I? I'll just hold it up here. Okay. Now, obviously, I can take this guy and I can put the South Pole toward it, right? And of course, the North Pole toward it, and the South Pole likes that, right? Now I can flip it over, and then of course, if I keep doing this, right, I ought to be able to make like some kind of motor, right? Whoops, it's not going around the right way, right? Okay, that's kind of fun. Isn't that fun? Yeah? Okay, I can also, this is kind of fun like this, right? I can stick this guy like, whoa, whoa, come back. Rewind. All right, here we go. It's like a remote control pivot. Yeah, this is like a Kaiser. Do you guys ever go to like Interstate Kaiser and they've got the little tables with the sand and the bulldozers and the magnets under there? I play with those things. I love those little tables where you can, like, you know, it's like, in fact, when we do a lab later, we're actually going to set up a little thing like that, right? That's kind of fun. Okay. All right. Okay, and then we've got the iron filings, and I think the last time you saw this, right, I said electric fields look like this, right? But now I'm going to do this and say this is a magnetic field, right? And there are magnetic field lines, and these magnetic field lines go from north to south. So if you think about charge, it's sort of like an analogy. The North Pole is like positive, the South Pole is like negative, and sure enough, these guys, like little compass needles, are lining up to the magnetic field, okay? And they should be going, this is the North Pole here, right? So they're going from north to south. So magnetic fields go from north to south. So this is important concept 0, okay, is that a magnetic field is from north to south, okay? So if we have a North Pole magnet here, right, and we have a South Pole magnet here, and usually these magnets, this is why they have horseshoe magnets, right? Usually these magnets are like this. Okay? If we've got the North Pole there and the South Pole there, and sometimes, by the way, to generate the magnet, we've got coils of wire around this part, right? The magnetic field is from north to south. And the symbol for magnetic is B. Do you guys know why it's B? It's because we've gotten rid of this spelling, but the original spelling of magnetic was, right? It's a silent B, just like any B next to an M is silent, like lamb and comb and stuff like that, right? Okay, so it used to be, and some people actually, it was originally pronounced, so people said bemagnetic, right? And then it became magnetic, like lamb, comb, right? And then, yeah, okay, yeah. Right, and then this was by the way the downfall of my youth. Okay, whereas we can have a monopole, a charge monopole. A monopole just means we can have an isolated positive charge. I can take electrons off of something and then set it over there. I can leave it in Vermont, and come back, and as long as the charge doesn't leak onto it or off of it, the charge is still there. Right? We can have electric monopoles. There is no magnetic monopole. And I discovered this as a child because I had designed a perpetual motion machine that, like, in 5th grade or something like that, that depended on me getting a magnetic monopole. It wouldn't have worked either.